Hi, my name is Yasiru Jayasooriya and I am from Sydney, New South Wales. I will share with you some of my insights for a sequences problem from the AMC. This is 2016 Senior Problem 20. The increasing sequence of positive integers 1, 2, 4 and so on has the property that each term from the third onwards is the next positive integer which is not equal to the sum of any two previous terms of the sequence. How many terms of the sequence are less than 2016? The options are A. 1008, B. 63, C. 11, D. 15, and E. 673. Whoa, that was quite a lot to take in. It would be good if we could really get a feel for what this problem is asking. How about we try to calculate the next few terms of the sequence? We have the first three terms, 1, 2, and 4. The sum of these two terms is 3. The sum of these two terms is 6, and the sum of these two terms is 5. We also have 1 and itself give 2, 2 and itself give 4, and 4 and itself give 8. If we go back to the problem statement, we know that the fourth term is the next positive integer after 4, which is not equal to any of the first three terms. This means that the fourth term cannot be 5, 6, or 8. This means that the smallest number we are allowed to slot in is 7. If we repeat this process, we find that the 6th, 7th, and 8th terms are 13, 16, and 19. Hey, look what we have here. From the number 4 onwards, the subsequent terms seem to be going up by 3. So you might guess that the pattern of going up by 3 each time continues until infinity. And this is a multiple choice question, so yay, you don't have to write a rigorous proof of why the pattern continues until infinity. So if you're feeling lucky, you can have a shot at guessing one of the options based on the pattern. But how can we be sure that the pattern continues? What if, in a 1 in a million chance, the pattern stops working and the sequence starts another pattern instead? To be 100% sure, we can use the proof technique of strong mathematical induction. We can start by assuming that the pattern we conjectured will in fact continue until some point. That means we assume that the sequence will be 1, 2, 4, 7, 10, 13, up to 3m plus 1 for some positive integer m. Note that the 3m plus 1 here comes from the fact that if we keep on adding 3 to a number that is 1 more than a multiple of 3, the result will still be 1 more than a multiple of 3. We can see that our assumption is true for m equals 4 since 3m plus 1 will equal 13, and we know already that the first 6 terms of the sequence are 1, 2, 4, 7, 10, 13. This means that our assumption is true. So we can make m equals 4 the base case of our mathematical induction. Now let's assume that the problem is true, or the assumption is true, for some value of m that is at least 4. Then we can find the next term in the sequence. This will be at least 3m plus 2, as it must come after 3m plus 1. But if we add the term 1 and 3m plus 1, this and this, we get 3m plus 2. And also, if we add 2 with 3m plus 1, we get 3m plus 3. This means that the next term cannot be 3m plus 2 or 3m plus 3. What about 3m plus 4? This is 1 more than a multiple of 3. Also, all of these terms are one more than a multiple of 3, except for 2. If we add two terms that are one more than a multiple of 3 together, we will get a number that is 2 more than a multiple of 3, which cannot be 3n plus 4. If we add the number 2 with any other term apart from 2 itself, our result will be a multiple of 3, so it cannot be 3n plus 4. If we add 2 plus itself, we get 4, but this is less than 3n plus 4, as m is at least 4. So none of these numbers can be 3n plus 4. This means we can never make 3n plus 4 by adding 2 of these terms. So 3n plus 4 must be the next term in the sequence. And since 3n plus 4 is 3 more than 3n plus 1, that means our pattern continues. So we can conclude with strong mathematical induction that the terms in the sequence go 1, 2, 4, 7, 10, 13, 16, 19, and so on until infinity, where each term from 4 onwards is 3 more than the previous term. The original question asks how many terms in the sequence are less than 2016 or at most 2015. Note that 2013 divided by 3 is equal to 671. This means that 2014 is equal to 1 more than a multiple of 3. So it is a term in the sequence. The term after 2014 is 2017. But it is after 2015, so we don't count it. So all the terms less than 2016 are 1, 2, 4, 7, 10, 13, ... until 2011 and 2014. Now consider another sequence going 3, 6, 9, 12, ... 20, 13. The number of terms in this sequence is 2013 divided by 3 is equal to 671. Now, shift all the terms in this sequence up by 1 to get a new sequence. 4, 7, 10, 13, ... 2014. There will also be 671 terms in this sequence. But the original sequence is formed by adding the numbers 1 and 2 at the start of this sequence. So the number of terms in the original sequence will be 2 plus 671, that is 673. This means that the answer is E. And there you have it. That was quite a marathon, but we got through it in the end. Hope you enjoyed this video.